Okay, so as it is now, from this particular one, as you can see here, this is half T naught naught, and done. So it means I'm just going to, for these two factors here, write for the first T naught naught conjugate, k sub I, k sub j, multiplied by Tij. For the second T naught naught, k sub iota, k sub k, then the energy momentum tensor Lk or iota k. Now it continues. The only thing here, of course, you can see is that in my next step, instead of having jj here, I leave the first j and write the next j as a k. I hope I'm talking about the right. Yeah, so this is j and this is k. So what it means is, instead of just having k iota m, I now multiply further with chronicle delta jk, to denote, of course, that these two are the same. So I think, of course, it's the next thing I will have to do for the next term. I have I here, then again I multiply with some chronicle delta instead of just m. Okay, so I guess on this term in particular, I have changed m to iota. Yes, I changed m to iota, and that's what it is here. Iota is here. Then instead of iota, what I will have here, for instance, is one of the i's become a k. So I guess, okay, what I did actually was to change m to, this is, okay, sorry please. This is I, this is I. I changed one of the i's to j, and eventually, the second I made a k, and this is what I get. Then the other chronicle delta, which should have been for m iota, or I just left I. So I think what I did was to actually interchange between m and I. Well, they are dummy indices. So the first thing was to interchange between m and I, and that is what I have here. So that instead of km, I have ki, and then the m here becomes an I, and then the m becomes a j. On changing that, just making it a j and making the second I a k, so that I have this chronicle delta attached to that. This next term needs no further evaluation or manipulation at this moment, so I just leave that as that. The next thing I do, of course, is, okay, I think I will have to make further changes here. I change the m's here to k, so which is why this will become k, and I'm supposed to have another k here, but then this chronicle delta will be iota k, and this is what I have. However, one of the k's here I'm going to change to a j, just so that I can multiply with the chronicle delta of iota k. Because if you recall, this is m and m, but which I've changed to a k. But then if that is the case, then it means that what I have as a chronicle delta here would be the fact that this is iota k and I and j. If you recall, this is the factor we have obtained from the one with Tii originally. Of course, I didn't erase that, so it's still here. This is Tii. These two are the same. All the indices are the same. So all this is saying is, for instance, if you say that I is equal to j and iota is equal to k, they are all the same, being dummy indices. And that is just for the first term in that bracket. So it continues again in this next term. What I've done is simply again to have changed. And please, oh, I didn't take note of this. So the T naught naught here, let me just make a notation. The T naught naught here, as we derived it then when we talked about the TT gauge, is something like this all over omega squared, TJI. But again, I think I've recalled saying that I might as well, so let me this time around put the I down, make it as hat, and J down and hat. This is TJI. So, which is why the omegas are not following us, if you notice. So, instead, because I'm using the unit vectors. So, okay, let me see that. This is just from here. Exactly. So, this next term here that I'm talking about is from here. And like I've stated before, I think this is a mistake, please. I have to. Okay, so as it is now, I apparently missed a T, which of course I'm sandwiching here. What actually happened is this is minus of k rho sigma. That's what it should have been. I decided to change them, both rho and sigma, to iota k, and this is what I have here. The I am here, by the way, which of course, or iota m, you can see also multiplied by a chronicle delta of iota m. I change also again to I and j respectively. My reason for doing this is just, as you can see, I'm getting some Tij, iota k, Tij, iota k. I just want to make sure I get them all to be of that form so that I can pull that out of the bracket with some factors left in the bracket. So the next step again, I perform the same kind of changes or interchanges, and that is what I continue with. I'm guessing, yeah, this is the very last one. All I've done there, I believe, is to have changed root sigma to ij again, so that again, what I have here is ij instead of root sigma. And then k here, I left k, but then changed the n there to iota, and that's what I get. So in the next step, again, if you take a good look at this, I just write everything again. Nothing much changed, unless, of course, that I identify the fact that this is the same with this. These two terms here add up, as you can see for yourself. And so if they do add up, what I'm going to do is to add them together in my next step. But then I'm going to jump maybe 1 or 2 steps. Yeah, if I add these two up, take note of the fact that this is Tij conjugate T iota K, Tij conjugate T iota J, iota K. The same thing here. Also, it means I can really pull that out of the bracket. And then those two terms which I said are the same, I've combined to minus 2 down. And the next thing, of course, you can see is here I want to make an interchange between m and iota and j and I. And this is possible because, remember, there's a factor out there multiplying this term. And so it's multiplying all the terms actually. But if I'm considering these two factors, then all these things I'm talking about are dummy indices. And so I can interchange between one and the other. My reason for doing that again is just to make sure that everything aligns in the way that I can manipulate it. For instance, I'm making that interchange. I'm going to have in the next term, I think this is what it should be. What I have then is something like case of Jm. And here, these are just purely chronicle deltas. This is the first term. So all I've got here, for instance, is some K's and M's and chronicle deltas. And one of the main reasons also, I must confess, is the fact that by the end of the day, it will look just exactly, and I want to convince you by doing this, it will look just exactly like the expression that we use. If you remember one of our presentations, I think we call that symmetry integrals. I can't remember exactly, but we did that. We call that symmetry integrals, and we did solve an example in which the expression here in the bracket is equal to this. And we said we have copied this from Weinberg's very good book, Gravitation and Cosmological Principle. We use that an example of one of the integrals we could solve using the property of the integrals, or the integral identities, if you like, the integral identities that we talked about in that presentation. So I wanted it to look just like it, just to avoid having to work this or talk about this all from the beginning. So in the end, what I have outside is this, but what is there in the bracket, as which we call this, is equal to the whole of that. The only difference, of course, here in this expression, I'm going to try to replace the k hats with x hats. But if you remember in that expression, what we used actually wasn't even n hat. I can't remember if it was n hat. It was either n throughout. So what we had was something like ni, nj's, and nk's multiplying themselves. So I just want to let you know that it's all the same. Whether it had hat on it or not, these are just unit vectors. So if you were to write this expression in terms of n, that's for every k of this here, you replace them. That's, for instance, instead of ni, k hat I write something like n sub I here, n sub j, n sub l, n sub n. If you were to do this all across this expression, I believe that you will obtain exactly this expression that we use as our example in that problem. So again, going back to the formula that we started this whole work with, you can see, I think we'll release, but you might as well just go back to the previous presentation. But what it means is we wrote the expression in terms of this and some expression which is what we have called that. For instance, this is what we have called it. So we have just written the power per solid angle in terms of the space-space components of the energy momentum tensor. That is the main goal for this and the reason for which we are doing this. We have just succeeded in doing that, and more succinctly, this is what we've obtained. Where, of course, as you can see, this capital lambda sub ij, lm of x hat is given by this expression, like I said, okay, or this particular one here, in terms of x hats. Okay. We're going to get back to that in a moment, but at this moment I just want us to look at I just want us to take a look at something. First, we have the Fourier expansion of the energy momentum tensor in terms of, we could write it as this. And the next thing, of course, is that I can, for instance, decide to expand the right-hand side. Of what I'll do actually is to expand the exponential function. But I'll be doing this for the time-time component. If I did that for the not component, of course, what I'll have here also will be not. So, but then I'll have the exponential function to be something like this, expanding that. Using indices, what it means is that, for instance, if I were to use indices, let me make some space. If I were to use indices, it would mean something that k dot x I, this would just be the same thing like ki x prime sub I, something like that. And if it were to be squared, then it means k dot x, something like that squared, would be the same thing as ki, and then I may use kj, then prime I, prime j. Of course, my reason for that is just to make the identification of the fact that this is attached to this and that to that. In the end, again, it's just trying to follow the normal rule in tensor analysis, trying our best to avoid any index repeated more than twice. We have I, and jj, but we all know what this means, because by the end of the day, this means the dot product of this and this, and the dot product of that and that. And then by the end of the day, when we take the dot product, we discover that just the same thing. So by the end of the day, it's just the square. So I'm just saying that from this step to this step, what I've done is to have written everything in terms of these indices and not the vector form like you've seen it there. So the left-hand side, by the way, the T naught of x of k comma omega, if we recall again, we've had an expression where that is given by that. So in other words, we can write the left-hand side to be something like that, completely in terms of the spatial components, and we have eliminated the temporal components in this form. So that in the end, if I am to compare the coefficients or match the coefficients of Kij, which is why I carefully wrote this form in that, you can see, of course, I was supposed to have this multiplying the square of that times I squared, which is a minus, over 2 factorial. I carefully pull out these two factors, Kij and this Kij, so that comparing the coefficients of the two, I can say approximately that Tij, which is here, is equal to this omega squared multiplying this. So that's why I'm going to have minus omega squared over 2 times this integral, which is, by the way, what I have here. Of course, this expression should have continued if we had to take the expansion to higher order, but that is where we stop. And this is where we write this, and what we obtain actually here is what we call the mass tensor, or the quadruple moment. Of course, here, yeah, this is what we call the mass tensor, essentially. And what we're just trying to say is that we can write the spatial component of the energy momentum tensor in terms of the mass tensor in that form. So, which brings me back here to this expression. So, and this expression, we can see that I have here Tij conjugate of k comma omega, T iota m of k comma omega. These two, of course, I could simply just like I said, put in the result that we obtained just right now. It means I could write Tij with the indices on top to be minus omega squared. Well, it doesn't matter, these are all special components, so please just ignore that. But the important thing actually is that for Ti iota m also, I could write that to be, why do I have Ij all over the place here? So what I'm going to do here is one of these has to be iota m, and this also iota m. And so, if I multiply the two, because I have this and this, remember I have some omega squared here. So if I were to multiply the two, I have another omega squared, another omega squared. The minuses, of course, cancel. So I have omega raised to the power 6. Then the two multiply themselves. I have a 4 here multiplying the pi that was below. Then, of course, instead of q, Tij conjugate, I have q sub ij conjugate. Instead of Ti iota m, I have q sub iota m of omega. They're multiplied here by this expression, which is what we have here. With that, of course, that is what we intend to do next. Okay, then. So as I was saying, of course, yeah, we've seen the expression. A lot have been erased. So as you can see here, what we have here is the integral of this. And like I've talked a lot about this in the previous presentation. Just within this a few moments ago, please, again, if you feel confused about it, just rewind this. A few minutes past and you will find what I'm talking about. Well, I talked about this integral. I said we already performed that, and if you recall, of course, this factor here, because what I've done so far, however, is to multiply across by the angular frequency. So I'm finding now the total power, the average total power that is emitted by a gravitational wave. And we need this expression, the integral of this, which I said we worked out when we talked about symmetry integrals. And this is what we obtained, of course, if you recall. So now what we do next is just to substitute this expression. So I just take this expression and put here. And when I do that, the next thing, of course, I do is to multiply into this bracket or this expression with that, which is why I have it here and here also and here. So the next thing I do is to evaluate out the conical deltas. Yeah, of course, when I do that, you can take note of the factors. The pi cancel and the 2 cancels. This 2 here, and I get a 2, and then the 15 comes along. So this explains the g over 2 times 15. I'm not writing it as 30 just because, well, let's move on, but it's still the same thing anyway. Now, when we continue with this, it means every iota becomes an I, and that's what I have here. And this conical delta forces M to become J, and that's what I have. So the idea here is to write them all either in terms of II or JJ. Now this expression, I leave the II expressions alone and convert just this one all to I and J. And the same thing, of course, here I have I and J. But however, in this case, I here has a conical delta and J, so both have to be equal to, say, maybe I. And iota and M, like on this particular factor, also has to be equal. And so I made them all equal to I. On this last term here, I leave the I and J, and again, only iota and M here has to change to either I and J, and of course that is what I have got for this last term. So working with this, I can add this and this last term because they are just similar. And this, of course, the same thing except for the conjugate here. And then I'm making this modular squared. I'm still leaving this in this form. I'm saying this plus that gives me 12. I pull the 12 outside, but then again, because I have only minus 4 here, so I'm going to have minus 1 over 3 that should multiply this 4 to make this 12, since I'm pulling out 12 on this side. So what I have now left inside the bracket is this, minus 1 over 3 that. So in the end, what I obtain for this average emitted power is equal to this. And this we call the emitted gravitational radiation power in the quadrupole approximation. This, of course, was what we set out to find. And this is okay for a single frequency that could be written as a harmonic, in terms of some harmonic expansion of a single frequency, especially if you're talking about a binary star that is moving in a circular orbit. But if the orbit were to be elliptical, so that the frequency is a superposition of frequencies, one especially like we had for the case in which we had metric perturbation to be such kind of a superposition, then what will be better off, or what we will rather do then, is to write the mass tensor in terms of time or its time dependence. We can write it in time dependence in this form. Of course, you can see the only thing here is that I've written them all in this superposition. It's still Q of omega here and Q of omega here, but some time dependence have been added to it in terms of the exponents. So this being equal to that is the same thing as that. So, and in this case, then what we are going to do is to try to find a product of this third time derivatives of this mass tensor. If we perform that on this expression, of course, it's a simple exercise to see that when I differentiate this expression with respect to time thrice, this is what I obtain. But then if I am to take the time average of this expression, what I'm going to have, of course, is, supposing I just make some kind of distinction here, one is omega without a prime and the other one is an omega with a prime, then what I'm going to obtain is such an expression as this, just multiplying out, this is what I get. Now note these following expressions, and we're going to perform an approximation here, which when we average over long times that are compared with the longest of the bit periods, by bit periods we mean 1 over the difference here, modulus of omega minus omega prime. So for any situation for which omega is not equal to omega prime, and also we have this time, after a long period of, averaging after a long period of time, this term vanishes. In optomechanical or quantum optomechanics, well, this is usually referred to as rotating wave approximation. a situation whereby this exponential will double time, or you can say such exponential terms that are multiplied by this disappear when you average over such long periods or long time. And with that, you can see that this product, by the way, which is what we set out here to evaluate, becomes equal to that, with just these two middle terms vanishing. And all we have is this. Now we can do this here in this way. Well, you can try to say, if we set both k to be equal to I and iota to be equal to j, the idea here is just to make this, well, should I say, the same, that because you have here ij, the same thing of course occurs here. And since they are all the same, the first and second term will be the same in this case, then we're going to have 2 times of that, or 2 times one of them. And of course, if you are to divide by 2 on both sides, this is what you get. 1 over 2. Of course, if you note, we are going to have to make the same change here on the left-hand side. That's changing k to be I and iota to be j. However, if I make both I to be equal to j, that is for this term, I make I to be j, and k also to be equal to iota, and maybe also the same j, then of course I'm going to have the modulus of this squared, just like we had here in this case, I believe, this particular term here. When we had I and I here, it became the modulus of that squared. So what we are going to have in the end is the modulus of that squared, but this again will be twice. So that will be 2 times that. So by the end of the day, again, of course, I will have to do the same thing on the left-hand side. I will be equal to j, k will be equal to iota, and the 2 again, so it will be the modulus squared of that. So by the end of the day, I'm going to have the summation of omega squared modulus of this squared equal to half of that. What that means is I can come to this expression, this one which we found here, expand the bracket, and write it in this form. And as you can see, if I do that, then this term here that I've obtained, or that I have here, I can simply replace this by this. 1 over 2 that. And also this expression here that I have, or this expression which by the way is that just summation of this, which is the same thing as that, I can simply replace with that. So that in the next slide now I'm going to, so as it is right now, all we've done is, so just like I've said, both actually have 1 over 2, as you can see, these also have 1 over 2. So something is common, I pull out the 1 over 2 and this is what I get. That half cancels this. And then in CGS unit, this is what we've obtained. And this gives us, again, the emitted radiated power of gravitational waves. And at this, the quadrupole approximation, and this is what we have as the emitted power. So at this point then, we'll stop this presentation. See you again in the next one.